The goal of this lecture is to investigate the relationship among the different representations of an extensive form game. Initially, we focus on the concept of realization equivalence among mixed strategies. Suppose to have two mixed strategies of player high. They can be defined on some representations potentially different. Well, these two strategies are said realization equivalent if they lead to the same lottery over the outcomes for every pure strategy profile of the opponents. More precisely, when changing the strategy profile of the opponents of player high, the lottery over the outcomes induced by the first strategy of player high changes, as well as the lottery induced by the second strategy of player high. But these two lotteries are always the same. Since the lotteries are the same for every pure strategy profile of the opponents of player high, they are the same also for every mixed strategy of the opponents. Now we focus on behavioral strategies. We recall that they are defined on the agent form. Consider the example of the game tree reported in the picture and focus on the behavioral strategies of player 1. They prescribe the player to play uppercase L1 at information set 1.1 with probability 1, while the behavior at information sets 1.2 and 1.3 can be any. That is, it is sufficient that alpha and beta belong to the range 0,1. All these behavioral strategies are realization equivalent. Indeed, for every pure strategy of player 2, these strategies lead to the outcome with payoff vector 4,4 with probability 1. That is, all the strategies induce the same lottery over the outcomes. Realization equivalent behavioral strategies differ only in the information set that will be traversed with probability 0. In the picture, they differ at information set 1.2 and 1.3 that cannot be reached due to the fact that player 1 plays uppercase L1. We carry out a similar analysis with mixed strategies in the normal form representation. Consider the example in the picture of the game tree and the corresponding reduced normal form. Consider now the three strategies of player 1. Focus on the probability with which action uppercase L1 is played in the three strategies. The probability to reach the outcome 6,1 when player 2 plays lowercase L1 is the probability that player 1 plays uppercase L2 in some plan. In the first strategy, the plan uppercase R1, uppercase L2, uppercase L3 is played with probability 1/2, while the plan uppercase R1, uppercase L2, uppercase R3 with probability 0. Thus, the outcome 6,1 is reached with probability 1/2. In the second strategy, we have that the plan uppercase R1, uppercase L2, uppercase L3 is played with probability 0, while uppercase R1, uppercase L2, uppercase R3 with probability 1/2. Thus, the outcome 6,1 is reached with probability 1/2. In the last strategy, the plans uppercase R1, uppercase L2, uppercase L3, and uppercase R1, uppercase L2, uppercase R3 are played each with probability 1/4. Thus, also in this case, the outcome 6,1 is reached with probability 1/2. The same happens when we focus on action R2 of player 1. In all the three strategies, the probability that such an action is played is 1/2. The same happens when we focus on action uppercase L3 of player 1. That is, in all the three strategies, the probability that such an action is played is 1/2. And the same for action uppercase R3 of player 1. The question we pose is when two strategies defined on the reduced normal form are realization equivalent. The answer is when the condition in red in the slide is satisfied. That is, when for every possible action B, the cumulative probability that such an action is played over the plans A is the same. This means that the realization equivalent mixed strategies in the normal form also differ in the information sets traversed with probability strictly positive. The intuition is that since the space of the strategies of the normal form is exponentially larger than the space of the behavioral strategies, many strategies in the normal form are equivalent to each other. Now we focus on the relationship between mixed strategies in the reduced and normal form and behavioral strategies. Kuhn assures that, given a game with perfect recall, for every mixed strategy on the normal form, there is a behavioral strategy that is realization equivalent. In the slide, given a mixed strategy defined in the reduced and normal form, we provide a realization equivalent behavioral strategy. Consider the formula marked in blue. It is the bias rule applied to an information set. More precisely, consider that we are computing the behavioral strategy pi over action A. The numerator of the formula is the cumulative probability over all the plans to play action A. The denominator is the cumulative probability over all the plans to play the actions available at the information set in which action A is played. That is, it is the probability that the player plays at information set in which action A is available. Consider the example in the picture. Consider action uppercase L2. The cumulative probability over the plans to play action L2 is the sum of the probabilities over the plans uppercase R1, uppercase L2, uppercase L3, and the plan uppercase R1, uppercase L2, uppercase R3, marked in green in the picture. Consider the denominator. In this case, we need the cumulative probability to play all the actions that are available at information set in which the action uppercase L2 is available. In the formula, we define H as such an information set, that is, in this case, information set 1.2. The sum is defined on all the plans, including an action that is available at information set 1.2. These plans are those marked in green in the picture. The formula we applied is well defined if the information set H, that is, the information set in which the action A is available, is traversed with strictly positive probability. Suppose that the strategy of player 1 prescribes to play plan uppercase L1 star star with probability 1. Thus, information sets 1.2 and 1.3 are traversed with probability 0. In these cases, the behavioral strategy in all information sets traversed with 0 probability can be any. So, if we want to derive a behavioral strategy realization equivalent to a given mixed strategy of the reduced and normal form, we can find multiple, potentially infinite, behavioral strategies. All these strategies differ in the information sets reached with 0 probability. We focus now on the inverse problem, that is, from behavioral strategies to mixed strategies on the reduced and normal form. Here, given a behavioral strategy, we can find infinite equivalent mixed strategy of the reduced and normal form. A simple strategy, however, can be found as shown in the picture. Call P the plan whose probability we want to find. Consider all the action A included in the plan, P. The probability of P is given by the product of all the probabilities of the action A included in P, as reported in the picture. Here an example. Consider the plan uppercase R1, uppercase L2, uppercase R3. The probability is given by the product of the behavioral strategies on uppercase R1, uppercase L2, and uppercase R3. We show now that with imperfect recall, the equivalence between normal form strategies and behavioral strategies is not possible. We recall that a non-mixed strategy profile on the normal form gives a strictly positive probability to the outcome 2-1 in the picture that is achievable with action uppercase R1, lowercase r1, and uppercase L2. Well, consider the case reported in the picture, where player 1 randomizes uniformly at each information set, while player 2 plays lowercase r1 with probability 1. The lottery over the outcomes induced by this behavioral strategy profile is 1/2 over the outcome for 4, 1/4 over the outcome to 1, and 1/2 over the outcome for 2. This means that the outcome to 1 is reachable with strictly positive probability by means of this behavioral strategy, differently from what happens in the normal form. This shows that the lotteries over the outcomes achievable by means of behavioral strategies may be different from those that are achievable with normal form strategies. We focus now on the relationship between realization plans in the sequence form and behavioral strategies. Here we have a similar result of that by Kuhn for the relationship between normal and agent forms. Specifically, given a game with perfect recall, for every realization plan of the sequence form, there is a realization equivalent behavioral strategy of the agent form, and vice versa. Consider the example in the picture and the formula. Even in this case, we just need to apply the bias rule. Suppose that we want to find the behavioral strategy of an action A that is realization equivalent to a given realization plan. In the numerator of the bias rule, we have the probability that the sequence terminating with action A is played. In the denominator of the bias rule, we have the probability that the player reaches the information set in which A is played. Suppose that in the picture the action A is uppercase L2. The sequence terminating with action uppercase L2 is the sequence uppercase R1, uppercase L2. Consider the denominator. The sequence we need to consider here is uppercase R1. That is the sequence leading to the information set in which uppercase L2 is available. This holds if the sequence to use in the denominator is played with strictly positive probability. Otherwise, the behavioral strategy may be any. The problem of finding a realization plan that is equivalent to a given behavioral strategy, that is the inverse problem, can be solved by using the inverse of the above formula. Finally, we focus on the remaining case, that is, from the normal form to the sequence form. Here we have a stronger result than that by Kuhn for the relationship between the normal and the agent forms. Specifically, both in games with and without perfect recall, for every realization plan of the sequence form, there is a realization equivalent mixed strategy of the normal form, and vice versa. Consider the example in the picture and the formula. Given a mixed strategy of the reduced normal form, the realization plan defined on a sequence QA, where A extend Q, can be easily found as the cumulative probability over all the plans that include action A. This shows that the relationship between the strategy of the normal form and of the sequence form is linear, differently from the relationship studied before. Focus on the reverse problem, that is, deriving a mixed strategy of the normal form that is equivalent to a given realization plan of the sequence form. The formula marked in red provides a linear system with an exponential number of variables and a linear number of constraints. This means that, as already discussed before, there can be multiple, potentially infinite, mixed strategies on the normal form that are equivalent to a given realization plan. We ask whether we can find a simple strategy without solving such a linear system that is exponentially large. The answer is yes. It is sufficient to use the second formula in red. That is, the probability of a plan P is given by the product of all the probabilities associated with the terminal sequences included in the plan. Q over line is the set of terminal sequences. For instance, if we want to derive the probability of plan uppercase R1, uppercase L2, uppercase L3, we need to make the product of the realization plans on uppercase R1, uppercase L2, and uppercase R1, uppercase L3. That are the terminal sequences included in the plan.